morning, students. I'm Chaitanya, Assistant Professor in Mathematics, Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, our topic of discussion is singular value decomposition of a 2 by 2 matrix as well as a 3 by 2 matrix. So, let us look into the details with the help of the next slide. So, first let us recap what is a singular value decomposition of a matrix. So, any matrix, whether it is a square or rectangular or zero or non-zero, any non-zero matrix, which is of order m by n, can be split into product of three matrices, namely u into d into v transpose. Okay, any non-zero matrix of order m by n can be split into product of three matrices u into d into v transpose, where u comma v are orthogonal, even orthonormal. In fact, they are orthonormal, and D is a diagonal matrix. D is diagonal matrix. Okay, so this kind of decomposition of the matrix A, like a product of three matrices U into D into V transpose, is called singular value decomposition, where U and V are orthonormal matrices and D is a diagonal matrix. Let us look into the meaning of this orthonormal matrices. And so A can be written as the product of three matrices U into D into V transpose, where U is orthonormal and D is diagonal and V is also orthonormal. Okay, let us look into the meaning of an orthonormal matrix. U is said to be orthonormal matrix. Say U contains the vectors U1, U2, U3. Okay, then this matrix is said to be orthonormal if the product of each pair U1 dot U2 is 0, U2 dot U3 is 0, and U1 dot U3 is 0. At the same time, norm U1 is equal to 1, norm U2 is equal to 1, norm U3 is equal to 1. So every column vector is a unit vector and every pair of vectors are orthogonal to each other. This kind of matrix is called orthonormal matrix. So U and V are orthonormal matrix and D is a diagonal matrix. Now, according to the procedure of calculating U and V, U, D, V, etc., we depend on eigenvalues and eigenvalues and eigenvectors. So, we'll take the help of eigenvalues and eigenvectors in order to calculate U, D and V transpose. Okay, and we also seen that this singular value decomposition is very important in machine learning algorithms for dimensionality reduction as well as image processing. Okay, now let us move to the next slide. So this is just outlay picture of the matrix decomposition, singular value decomposition. This is the matrix here. This is U, this is the diagonal matrix, and this is V. Here we have to remember that U is formed with eigenvectors and V is formed with eigenvectors, and this is formed with eigenvalues. So what do you observe? The first matrix is formed with eigenvectors, second matrix will be formed with eigenvalues, third matrix again formed with eigenvectors. Eigenvalues of some matrix and eigenvectors of some matrix related to A. Okay, let us take a problem. First we'll see a problem of 2 by 2 matrix, how to decompose it into singular value decomposition. Okay, and then we'll go to a 3 by 2 matrix. So, just here one important point we have to note. The A is singular. You know what is singular matrix? That A is 0, then we call A is singular. So if A is a singular matrix, then definitely at least one eigenvalue Wi or one entry of the middle diagonal matrix should be 0. That is what we have to know. Okay, and also when we decompose A is equal to U into D into V transpose, okay, when the size is M by N, automatically this size will be M by R, this size will be R by R, this size will be R by N. Like that we'll decompose. Okay, so this is what summarized in these points. Okay, now so SVD is one of several techniques that can be used to reduce the dimensionality. That is the when we have a huge data set, we can reduce its dimension, that is number of columns, and we can simplify the data set and without disturbing the essence, and so that it will occupy the less storage and it saves our time. This is called reduction of dimensionality. That is done by using singular value decomposition. Okay, and SVD can be used for dimensionality reduction. It is often used in digital signal processing for noise reduction, image compression, and other areas. Even to reduce the noise in the communication channel, you can use SVD. Similarly, image compression also will use SVD. Now we are going to a problem. Here we are having a matrix A which is given by 4, 0, 3, minus. So we have a 2 by 2 matrix. We have a 2 by 2 matrix 4, 0, 3, minus 5. Okay. Now we are going to decompose this A is into the form U, D, V transpose. Okay. Where U is some orthonormal matrix and D is a diagonal matrix. V is also an orthonormal matrix. Let us see how we are going to achieve that. First, let us consider the matrix A 4, 0, 0, 4, 0, 3, minus 5. Okay, now we are calculating as a first part of singular value decomposition, we are calculating A into A transpose. A into A transpose. What is A? Let us write here 4, 0, and 3, minus 5. Let us check. 4, 0, 3, minus 5. So we are taking A, its transpose is 4, 3, 0, minus 5. 4, 3, 0, minus 5. Now let us multiply this matrix. Then we get 16, 12, 12, 34. Right? So that is the matrix we have written here. This is the matrix 16, 12, 12, 34. Now let us consider the characteristic equation of this matrix A into A transpose. So yes, what is characteristic equation? Let us recap. Characteristic equation of a matrix B is det of B minus lambda I is equal to 0. This is called characteristic equation. So for A into A transpose, we have characteristic equation A into A transpose det of A into A transpose minus lambda. So when we write the det of A into A transpose minus lambda is equal to 0, it is nothing but 16 minus lambda, 16 minus lambda, 12, 12, 34 minus lambda. Because here you can observe 16, 12, 12, 34. So A into A transpose minus lambda I means det of the matrix 16 minus lambda, 12, 12, 34 minus lambda is equals to 0. Okay. Now let us expand this det by using AD minus BC is equal to 0. Let us expand the det by using the formula AD minus BC, which is equal to 0. We get an equation 16 minus lambda into 34 minus lambda minus 144 is equal to 0. After simplifying this, we'll get a polynomial which is nothing but lambda square minus 50 lambda plus 400 is equal to 0. Okay. Now let us decompose this into factorization. Now once we factorize this, we can write it as minus 400 means 10 lambda minus 40 lambda we can decompose. So we get lambda of lambda minus 10, okay, and minus 40 lambda minus 10 is equals to 0. That is why eigenvalues are lambda is equal to 10 comma 40. Now we have successfully found the eigenvalues, and these eigenvalues are the eigenvalues of A into A transpose. So we found the eigenvalues of A into A transpose as lambda is equal to 10 comma 40. Okay, this is the step where we have arrived in. Okay, now let us go to the next part. Now we are going to find eigenvector of, I am writing here, eigenvector of A into A transpose at lambda is equal to 40. Okay, so what is for that we must take the matrix A into A transpose minus 40i. That means we have substituted lambda is equal to 40. We know this is our characteristic matrix A into A transpose minus lambda, where we are substituting lambda is equal to 40. Then the matrix becomes 16, and let us check the matrix. 16, 12, 12, 34. 16 minus 40, 12, 12, 34 minus 40. This is the resultant matrix. And once we subtract, we get minus 24, 12, 12 minus 6. Okay, and when we divide it with the first row with 12 table and second row with the minus 6 table, we get minus 2, 1, minus 2, 1. Okay, and hence we observe that the two rows are identical, and hence we can write an equation minus 2x1 plus x2 is equal to 0 with the help of the first row. With the help of this row, we can write this equation minus 2x1 plus 1x2 is equal to 0. Okay, now let us put x2 is equal to 1 in default. To find out the values, we are choosing x2 is equal to 1. Minus 2x1 plus 1 is equal to 0. x1 is equal to minus 1 by 2. So what do we observe? We got when we put x2 is equal to 1, we got x1 is equal to minus 1 by 2. That means we got x1, x2, the vector x1, x2 as minus 1 by 2 into 1. Okay, now once we, let us say this is x, let us call this vector as capital X. Okay, now let us calculate norm x. Norm x is nothing but root of x1 square plus x2 square. That is root of minus 1 by 2 square plus 1 square, and hence you will get 1.11h. Okay, so what we have done, we started with A into A transpose minus 40i. Our aim is to calculate eigenvector with respect to lambda is equal to 40 for the matrix A into A transpose. So A into A transpose minus 40i. This is the resultant matrix. And after doing the row operations, we get two rows identical. So we can consider only one row. We are considering the first row. Minus 2x1 plus x2 is equal to 0. That is the equation we have written here. And we have taken default x2 is equal to 1. We have taken default x2 is equal to 1, and hence x1 is minus 1 by 2. So we got x1 value minus 1 by 2, x2 value 1, which is called the vector x. We have calculated norm x, which is root of minus 1 by 2 whole square plus 1 square, which is 1.118. Okay, now after doing this, we are going to calculate normalized eigenvector. Normalized eigenvector of x1. That means if x1 is an eigenvector, then x1 bar is its normalized version of eigenvector. Let us calculate x1 bar. For this, we need norm x1. So first norm x1 we already calculated norm x1 as 1.118. Now x1 bar is nothing but the vector minus 1 by 2 divided by 1.118 and 1 divided by 1.118, and hence we get a new vector which is called x1. Okay, it's just nothing but 0.4472 and 0.894. You can easily calculate, you can easily observe. That means we are dividing. Initially, we have x1 is equal to minus 1 by 2, 1. So we are dividing every element with its norm. Minus 1 by 2 by 1.118, 1 by 1.118. And hence we got new vector which is called normalized eigenvector, x1 bar. Okay. And for the time sake, we are naming it as u1. So this is our. Okay. So after understanding this, we are going to calculate the next eigenvector corresponding to the next eigenvalue 10. Okay. So moving to the next slide. So here we are calculating the same way. We have another eigenvalue which is nothing but lambda is equal to 10, and corresponding to this eigenvalue lambda is equal to 10, we can take A into A transpose minus 10i, which is nothing but 16 minus 10 and 16 minus 10, 12, 12 and 34 minus 10. Okay, so what we get 6, 12, 12, 24. Similarly, we get this as 1, 2, 1, 2. So eigenvector is x1 plus 2x2. Eigenequation is x1 plus 2x2 is equal to 0. This is from this row we are writing because these two are identical. We can take only one row. 1x1 plus 2x2 is equal to 0. Now choose default. By default, choose x2 is equal to 1. Then x1 is equal to minus 2. So our vector is x1 x2 is minus 2 1. Okay, this is our vector x. Norm x is nothing but root of minus 2 whole square plus 1 square. That is root 5. So the corresponding normalized vector x bar is given by minus 2 by root 5 and 1 by root 5, which is nothing but 0 minus 0.8944, 0.447. Okay, this is for the time sake we denote with u2. So this is our u2. Okay. So in this way, we can calculate the eigenvalues and eigenvectors for the matrix A into A transpose. Now I am summarizing the things what we have done so far. Yes. So far, first we have calculated A into A transpose, which is 16, 12, 12, 34. Then we calculated eigenvalues for it, that is 10, 40. And we have calculated first the eigenvector corresponding to 40. That is u1. u1 is the eigenvector corresponding to 40 and u2 the eigenvector corresponding to 10. Lambda is equal to 10. Okay, this is corresponding to lambda is equal to 40. This is corresponding to lambda is equal to 10. And we have to understand that both u1 u2 are normalized. That means unit vectors. And also you can easily observe that u1 dot u2 will be 0. Okay, this is automatically happens. Okay, so with this we have completed one part of the problem. Now we are going to the next stage. Now we are going to calculate A transpose into A. A transpose into A is nothing but the matrix actually we are given with is 4, 0, 3 minus 5, right? So once we calculate 4, 0, 3 minus 5, okay, this is our A, and A transpose is 4, 3, 0 minus 5, and we calculate A transpose into A, we get 25 minus 15 minus 15, 24. Okay, so that is what written here, 25 minus 15 minus 15, 25. Now we can write the characteristic matrix A transpose A minus lambda I. That is 25 minus lambda minus 15 minus 15, 25 minus lambda. Okay, after that we can calculate the det, that the characteristic polynomial, that is det of A transpose A minus lambda I, and equating to 0, we get an equation which is represented with this here. Okay, after expanding that, we get an equation again same, lambda square minus 50 lambda plus 400 is equal to 0, and hence the eigenvalues are nothing but 10 comma 40 again. So eigenvalues of A transpose A is equal to 10 comma 40. Surprisingly, already in the previous part we got eigenvalues of A into A transpose is also 10 comma 40. This has happened because A is symmetric. When A is symmetric, or upper triangle or lower triangle, so in that cases we can observe that the eigenvalues will be same for A into A transpose as well as A transpose into A. Okay, now after getting these eigenvalues, just like the previous way, we can calculate A transpose A minus 10i, and hence we get an eigenvector. Similarly, A transpose A minus 40i, we get another eigenvector. We call them as V1 and V2. You can find them, okay, here. So this is V1. This is V1 corresponding to the eigenvector lambda is equal to 10. Okay, this is the norm. Okay, and this is V2. This is V2, which is corresponding to lambda is equal to 40. Okay, now we got the eigenvectors V1, V2 for A transpose into A. Already we got U1, U2 for the matrix A into A transpose. So we found eigenvectors for both matrices A into A transpose as well as A transpose into A. Also, we found that the eigenvalues of A into A transpose is 10 comma 40, and eigenvalues for A transpose into A is also 10 comma 40. Okay, this is what we have done so far. Now we are going to calculate the third matrix. That is, we are going to calculate the third matrix. That is the diagonal matrix D. How we calculate this? I told you already that this is a diagonal matrix. Diagonal matrix means it should be like alpha 1, 0, 0, alpha. Okay. How to calculate these two elements? Simple. First, let us check what are the eigenvalues. Always see eigenvalues of A transpose A and A into A transpose will always same. Eigenvalues are same, but not eigenvectors. Okay. So why eigenvalues will be same means because A into A transpose whole transpose is A into A into A transpose whole transpose is A transpose into A, or you can say this is A into A transpose, and hence this is symmetric. Okay, that is why, and also A transpose into A is also symmetric. You can understand both are symmetric. So that is why eigenvalues will coincide with each other. Always the eigenvalues of A transpose into A, comma A into A transpose always coincide with each other. That is why in this problem also we got 10 comma 40 for both the matrices. Okay, now right, after doing this we are going to calculate the diagonal matrix D, or you can call it singular matrix D, with the formula root of lambda 1 0 0 root of lambda 2. What are lambda 1, lambda 2? Nothing but eigenvalues of A into A transpose. You got eigenvalue lambda 1 as 10 and another eigenvalue lambda 2 as 40. 10 comma 40 are our eigenvalues. So D becomes root 10, 0, 0, root 40. So which is nothing but 6.32456, 0, 0, 3.16228. Okay, so this is our diagonal matrix. And also we can write U as the matrix U1, U2. And we can also construct another matrix V as V1, V2. And we can consider the V transpose, that is the matrix V1, comma V2 whole transpose. And hence, okay, we arrive at these steps. Okay, this is our V1, V2. This is our matrix V. Already in the previous slide, we have calculated D and we have calculated U. Now, here we are seeing our matrix V. Now, this is an alternate way of calculating U from V or V from U. You can calculate, but those are not needed because we have calculated both of them independently. Now, we can verify that the product of U into sigma, or you can write D into V transpose, is approximately almost equals to our A. Okay, so you can easily verify this. What is U? We can write U here. And what is D? We can write it here. And we can write V transpose. And if you multiply these three things, you get almost all the matrix A by just small rounding up. You can easily verify. That means we have successfully decomposed A into product of three matrices U into D into V transpose, where D is diagonal matrix and U is orthonormal matrix and V is also an orthonormal matrix. And this is called singular value decomposition of a 2 by 2 matrix. Okay, now let us take an example of 3 by 2 matrix. How to decompose a 3 by 2 matrix into singular value decomposition. Let us understand the things with an example, with a solved example. Okay, with that we'll conclude the class. Yeah, here it is, the matrix. We are going to find the singular value decomposition of a 3 by 3 matrix. Sorry, I'm mistaken. It's not 3 by 2, it's a 3 by 3 matrix. Okay, so we are going to find the singular value decomposition of a 3 by 3 matrix. So the order is 3 rows, 3 columns, hence it is 3 by 3. Okay, the same matrix we have taken here. The A is equal to 1 to 1, 2, 3 to 1 to 1. And we are observing that first row and the third row is identical. So identical means we can say that det A is 0. Obviously, when we see identical rows or identical columns, automatically det A will be 0. Once det A is 0, A inverse doesn't exist. Okay, does not exist. But at the end, surprisingly, we are going to have an inverse for this matrix, which is non-singular, which is singular. Even though it is singular, we can find pseudo-inverse for this matrix, which is an approximate inverse. Of course, A inverse does not exist, but still we can find an approximate inverse, which is called pseudo-inverse. That will be discussed at the end of this problem. Okay, now. So here, as usual, just like in the previous problem, we are starting with A into A transpose. And we found that A into A transpose is this. And we are considering A into A transpose minus lambda, which is nothing but 6 minus lambda, 10, 6, 10, 17 minus lambda, 10, 6, 10, 6 minus lambda. Okay, this is our characteristic. This is called characteristic matrix. And the det of this matrix, which is equated to 0, gives us the characteristic equation which is represented in this equation. Okay, and if you expand the det carefully, along the first row, you will get this big equation, big polynomial equation, and you simplify, you will get the terms like this. Okay, and you further simplify, you will get this equation, and finally, by regrouping and adding, we get the equation lambda cube minus 29 lambda square plus 4 lambda is equal to 0. This is the equation we are going to get. Now just tell me what uh, what is the degree of this equation? Degree of this equation is 3 because it is a third degree polynomial. It is a third degree polynomial. The degree is 3 and hence it has 3 roots. It has 3 roots. Now those 3 roots are our eigenvalues. Okay, now we are going to find those 3 roots. So for that, let us write the equation neatly. Lambda cube minus 29 lambda square. Okay, lambda cube minus 29 lambda square plus 4 lambda is equal to 0. Once we take lambda common, lambda square minus 29 lambda plus 4 is equal to 0 and lambda is equal to 0. Okay, and the two values will be like this. Once you use calculator, you will get the roots, that is 0, 0.1385, 28.86. These are the roots of lambda cube minus 29 lambda square plus 4 lambda is equal to 0. For this equation, by using calculator, you will get the roots 0, 0.1385, 28.861 something. Okay, these are the eigenvalues. These are the eigenvalues of A into A transpose. Okay, now proceeding further, just like I have explained in the last problem, corresponding to the eigenvalue lambda is equal to 28.8614, we get the eigenvector v1 like this. And corresponding to the eigenvalue lambda is equal to 0, we get the eigenvector like this. And corresponding to the eigenvalue lambda is equal to 0.1385, we get the eigenvector like this. I'll explain how to calculate eigenvector with respect to lambda is equal to 0. Okay. With that, you can understand how to calculate the remaining two eigenvectors v1 and v2. Okay. Now, for that, let us first consider the matrix 6, 10, 6, 10, 17, 10, 6, 10, 6. Okay. So, I am considering A into A transpose, which is 6, 10, 6, 10, 17, 10, 6, 10, 6. This is our matrix. Now, A into A transpose minus lambda I. This is nothing but 6 minus lambda, 10, 6, 10, 17 minus lambda, 10, 6, 10, 6 minus lambda. Okay, this is our matrix. Now, let us substitute lambda is equal to 0. Substitute lambda is equal to 0. Then what we get? Then we get A into A transpose minus 0i is equal to 6 minus 0 means 6, 10, 6, 10, 17, 10, 6, 10, 6. Okay. So this is the matrix we are obtaining by substituting lambda is equal to 0. Now let us write the operation R3 tends to R3 minus R1. Then what happens? Then it becomes 6, 10, 6, 10, 17, 10, 0, 0, 0. Okay. And also, after writing, then we got two equations. Let us write them here. 6x1 plus 10x2 plus 6x3 is equal to 0. For this row, I am writing the equation. 6x1 plus 10x2 plus 6x3 is equal to 0. For second row, we can write 10x1 plus 17x2 plus 10x3 is equal to 0. Okay. So these are the two equations obtained by first row and second row. Okay. Now we can choose default x3 is equal to 1. Choose x3 is equal to 1 in default. Okay. Then the equations becomes 6x1 plus 10x2 is equal to minus 6. 10x1 plus 17x2 is equal to minus 10. After solving this, we get x1, x2 values. Okay, and already we have chosen x3 as 1, and after solving these two, we get x1, x2 values, and then normalizing, we get a vector. Good. Here you can see this is our x1, this is our x2. Okay, we can calculate the norm. We can calculate the norm of this vector, and by normalizing, okay, here we are calculating the norm 2.2006, and by dividing with the norm, by dividing every component with the norm, 1 by the norm, 1.686 by the norm, 1 by the norm, we get this is the normalized eigenvector. Similarly, for lambda is equal to the two other eigenvalues 28.816 and lambda is equal to other eigenvalue, okay, we get eigenvectors u2 and u3 like this. This is u2 corresponding to the eigenvalue lambda is equal to 28.816, and this is the eigenvector u3 corresponding to the third eigenvalue. Okay, in that way we can calculate. Now we are considering A transpose into A. Okay, where A, first let us write A 1 2 1 2 3 2 1 2 1. Its transpose 1 2 1 2 3 2 1 2. So because it is symmetric, we are observing both A and A transpose are same, and hence we get same characteristic equation, we get same eigenvalues, and hence we get same eigenvectors called v1, v2, v3. Eigenvalues are also same. What are those? 0, 28, 8.16, and the third eigenvalue, which I forgot, just I'll recollect. Third eigenvalue 0.1385. Third eigenvalue 0.1385. Okay, so these are the same eigenvalues, and eigenvectors will get v1, v2. Okay, now after getting this, okay, after getting this, we'll write the diagonal matrix D as root lambda 1 0 0 0 root lambda 2 0 0 0 root lambda 3. Okay, what are the eigenvalues we got? That is root 0 0 0 0 root 28.815 0 0 root of 1.385 or 0.1385. Sorry, I'm mistaken. It's a 0.1385. Okay, this is our D. And finally, okay, so this is our U, this is our V. Okay, how do we write it? How do we write U? U is nothing but U1, U2, U3 corresponding to the eigenvectors A into A transpose, and this is matrix V correspond with the help of vectors V1, V2, V3. Okay, from A transpose into A. Okay, and by multiplying, first we are multiplying U into D or U into sigma, whatever you would like to express. This is U, this is the diagonal matrix D. Okay, this is root to 28.815. This is root of 0.1385. This is root C. Okay, so we are multiplying those two matrices. We are multiplying those two matrices U and D. Then we get the result this. This is our U into D. Okay, now we are multiplying U into D with V transpose. This is U into D, this is V transpose. We are multiplying matrix. Matrix multiplication is first row, first column, next first row, second column, first row, third column, again second row, first column, second row, second column, second row, third column. Okay, and third row, first column, third row, second column, third row, third. Like that, once we proceed UD into V transpose, you get the answer this. And surprisingly, this is nothing but of A. So what do we observe when we multiply U into D into V transpose? We got the given matrix D. So we have successfully decomposed A into the product of three matrices U, D and V transpose, and this is called the singular value decomposition of the given matrix A. Now, one last question remains. That is, sir, we got U into A is equal to U into D into V transpose, okay, where U is 1, 2, 1, 2, 3, 2, 1, 2, 1. And we can easily understand that det K is 0 because the first row and the third row are identical. Det K is 0, hence A inverse does not exist. Right? Then you promised us that we can calculate, even though A inverse doesn't exist, we can calculate an approximate inverse called pseudo-inverse for this matrix. How to calculate that pseudo-inverse? By using singular value decomposition. Simple, the pseudo-inverse formula is given by the transpose, that is U transpose D star V. What is the formula? U transpose D star V. U transpose means you have to transpose this. V means you have to retranspose this. Okay, what is D star? Let us understand what is D star. D star is nothing but 1 by root lambda 1 0 0 0 1 by root lambda 2 0 0 0 1 by root lambda 3. That means if D is equal to root lambda 1 0 0 0 root lambda 2 0 0 0 root lambda 3, then D star is also a diagonal matrix formed with the reciprocals. Root lambda 1 becomes reciprocal, root lambda 2 becomes reciprocal of it, root lambda 3 becomes reciprocal of it. So D star is nothing but diagonal matrix formed with the reciprocals of these diagonal elements of D. And these are called singular matrix, and hence this is called singular value decomposition. And the product of U transpose D star V gives you a new matrix called, which is denoted by A power G, is called pseudo inverse. Okay, which is not exactly equal to A inverse, but it is approximately almost it acts as A inverse in solving system of equations with the help of A. Okay, so this is about the singular value decomposition of a 2 by 2 matrix as well as a 3 by 2 matrix, and the pseudo inverse of a rectangular matrix or non-singular matrix. Okay, with this I'd like to conclude the lesson, and on tomorrow we'll meet with next module. That is, we are going to comment the second module. We'll meet in that class, and thanks for your patience listening. Thank you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.